Just a quick video. I got a great question about ranking the intermolecular forces and also about what is soluble or not soluble in water. Okay, so I want to definitely make sure that you guys are super solid on this before your exam. Okay, so if you were ranking your intermolecular forces by strength, okay, the ones that we were talking about, you know, throughout this chapter have been your, so strong is going to be up top and weak is going to be at the bottom. So when we were talking about our strong one, we had hydrogen bonding, which is a bond between an F, an O, or an N bonding with a hydrogen, right? Fonkelbrish, the first three most electronegative elements bonding to a hydrogen. So an F bonding to a hydrogen, O bonding to a hydrogen, or an N bonding to a hydrogen, okay? Then we get dipole-dipole, which just means you do have a polar molecule, okay? And then you have London dispersion forces, okay? And this is for anything that's non-polar. All right, now these collectively, these three things are going to be seen in covalent stuff. Okay, these are in covalent molecules. Then even stronger above your covalent section is going to be ionic. Okay, so if I was ranking them strong to weak, okay, ionic's number one, hydrogen bonding, dipole-dipole, LDF, okay? So when you're going through these examples, you might be given a question like this, right? They will list 4 different molecules or some amount of different compounds, and then you'll have to rank them from something that has the highest boiling point down to the lowest boiling point, okay? So a lot of stuff to break down here, okay? First of all, before even thinking about, you know, what different forces act on these different molecules, I want you to first just think about what the heck is it asking you to do, okay? If something has a really high boiling point, that means it needs a lot of energy before the molecule itself is going to break apart. You need to give it a shirt ton of energy to break that molecule apart, to have it go from a solid to a liquid to a gas, right? For it to boil. If it has a really low boiling point, right, it will boil at very low temperatures. You don't need to give it a lot of energy for this thing to break apart. So things with a high boiling point are going to be very strongly held together, okay? And things with a low boiling point are held very weakly together, right? Because they can boil at very low temperatures. So you don't need a lot of energy to break them apart. Understanding what it's actually asking you to do is kind of key, right? And then now that I know, okay, the highest boiling point is going to be the thing that has the strongest bond. The lowest boiling point of these is going to be the thing that has the weakest bonds, okay? Knowing that, I can now go through and try and figure out what different forces will act on these specific molecules. So let me do that on a different page. So here are my 4 molecules, right? And if I'm trying to figure out what forces they have, I might need to actually draw them out, okay? But one of them kind of gives me a clear key right away as to what it is, okay? And that's right here, okay? Magnesium bromide, I have magnesium. This is a metal bonded to a non-metal. If I see a metal, I know right away this has to be ionic, right? All these others are going to be non-metals bonding to other non-metals. All these dudes are going to be covalent. So I have ionic, so boom, I found my strongest one already, okay? Which means I can come here and say for sure the thing that's going to be held the strongest together, the highest boiling point is going to be magnesium bromide, okay? Now I need to figure out what the heck to do with these 3. So, all right, we have water, CH2F2, and CO2, carbon dioxide, okay? If I was going to draw these things out, because you might need to help you figure out what the heck to do. Carbon's gonna bond to a hydrogen, another hydrogen, a fluorine, and another fluorine. Don't forget your lone pairs. And carbon dioxide, I'm gonna kind of angle it here. I'm running out of space. Okay, so here are my 3 different covalently bonded molecules. Now I need to figure out what to do, okay? Each one of these is a covalent molecule, so I know right away, no matter what, they're going to have London dispersion forces. Okay, now I need to figure out if they're polar or nonpolar. Okay, so I think about electronegativity. Oxygen is more electronegative than hydrogen. All right, so you're going to have these polar bonds. Since water is bent, you are going to get this delta minus side and a delta plus side. So it is in fact polar. And since it's polar, right, according to this wonderful thing, polar molecules have dipole-dipole forces. So this has LDF and dipole-dipole. I'm abbreviating. Hopefully that makes sense, okay? For this dude, okay, fluorine is much more electronegative. It's the most electronegative element, actually, right? So this is definitely going to be a polar bond. And this guy is a polar bond. So I'm going to have a delta minus part of my molecule on this side, which means I'm going to have a delta plus part of my molecule on this side, which means this is also polar, which means this also has dipole-dipole forces. Okay. Of course, oxygen is more electronegative than carbon, so it's going to pull the electrons this way, and this oxygen is going to pull the electrons this way. And this is the catch, right? Because carbon dioxide is actually nonpolar. These poles cancel each other out. Right? I don't have a delta minus on this side and a delta minus on this side, okay? I'd have to have a delta minus and then a delta plus on the other side. So this is nonpolar. The pull of these kind of electronegativity goes in exact opposite directions because it's linear. So this is nonpolar, so it only has London dispersion forces. I don't know if that's more clear. This is polar, and this is also polar, okay? So this is nonpolar. This is going to be my weakest. And I'll label this strongest. Okay, so if I was going back to my ranking system, okay, I know magnesium bromide is going to be the strongest, and I know my carbon dioxide is going to be the weakest, okay, my lowest, right, because it's nonpolar. Now I need to figure out which one of these guys wins, okay, which one of these guys is going to have hydrogen bonding, okay, and if you're looking at it, you're like, oh my God, they both have hydrogens, and they're both polar, so they both have hydrogen bonding? No, okay? Please remember that hydrogen bonding is only a hydrogen bonded to a fluorine, a hydrogen bonded to an oxygen, or a hydrogen, I'll have that cut out, bonded to a nitrogen, right? FON, all right? The first 3 most electronegative elements. So, does this have a hydrogen bonded to an oxygen? Why, yes, it does. This will also have hydrogen bonding. Does this have a hydrogen bonded to a fluorine? No, this only has hydrogen bonded to carbon, hydrogen bonded to carbon. Yes, there are fluorines in this molecule, but the hydrogens are not bonded to it. So that means no, this does not have hydrogen bonding, okay? Which means between the 2 of them, water is stronger or held together more strongly than this guy, okay? So if I was going to rank them, all right, the strongest would be my ionic. The next strongest is going to be the water. The next strongest would be your polar, okay? Polar with dipole-dipole, but not hydrogen bonding. H2F2. And then your weakest is your nonpolar, okay? Okay, so I hope that helps, just trying to figure out like how to rank the different molecules. Good luck.